that. Yeah, fantastic. So our codomain here is going to be all of the possible values of the outputs, all possible values of y, whereas the range is the values of y that we actually see. Fantastic example that we could look at here is we could think of a very, very simple function. Maybe the domain is just the set that is the letter A. Maybe our codomain is going to be the letters B and C, and maybe our function f takes A and maps it to B. All right. Notice here that within our codomain, there is a value that does not get mapped to. That's okay as long as it is our codomain. That's fine. We're okay with that. Sometimes there are things that live in our set that we just don't hit. That is not a problem. When this is a problem is when we take the inverse of this particular function, or when we try to take the inverse of this particular function. What does the inverse ask us to do? Well, it asks us to swap the domain and codomain. Our inputs and our outputs are going to trade places. And so what are we going to end up with? Well, before we were plugging in A and getting an output of B. Now we're pulling from that codomain. Now we're pulling from that space that is B and C, and we are plugging in towards trying to get something from that domain, or what was that domain in this case, that set A. Part of this is very simple, right? For instance, F inverse of B, which is to say that this inverse mapping that is now taking B in as an input is going to spit out what as an output? What did we say? A. It's going to spit out A as an output. Before, we were plugging in A and getting B. Now, the inverse, we are plugging in B and getting A. That's fine. That's great. That's fantastic that we get to do that. Where we run into a problem is when we try to do the same thing with C, when we try to take F inverse of C. Why is this a problem? There's nothing to go. C doesn't have anywhere to go. C doesn't get mapped to in our original function. And so when we try to trace back and ask the question, what is the input that would spit out C? There is none. There isn't an answer here. And the fact that there isn't an answer here is a problem. This is actually fairly problematic. Okay. Good news is that it is a problem with an easy solution. And that easy solution is just to restrict our range, or specifically restrict our codomain to only look at the range. It's a little bit nuanced, but essentially we're just going to throw away C. Right? We say, well, C doesn't get mapped to. I don't really need it. We're going to throw away C. It's not going to be a part of my inverses domain. And as a result, we're not even able to ask the question, what is F inverse of C? It never even comes up. Okay, so one little piece of nuance here. Sometimes we have to chuck values that could have been outputs. We have to restrict that range, or specifically we have to restrict the codomain to match the range. Fantastic. There is going to be another issue that we run into, though. So we understand to a fairly good degree what a function is, what a function requires. What is special about a function that makes it different from like any standard kind of mapping, any generic relation? What about functions makes them functions? Exactly. We have no repeated values of x. Plugging in a value of x, you know exactly where you are going to. Okay, we are now taking the inverse of our function, which is to say our x's and our y's are switching places. So we still can't have repeating values of x. Otherwise, the thing that we're starting with wouldn't be a function. But now, what do we also need to worry about? We also now need to worry about repeated values of y. Because when we do this kind of switch, what we will see is that repeated values of y, when we take their inverse, become repeated values of x. When the x's and the y's switch, y's that show up more than once turn into x's that show up more than once. So again, within the context of our function, it's fine to have repeated values of y. It's not okay to have repeated values of y for a function that is invertible, for a function that we can actually take the inverse of. Okay, so let's look at just a quick example here. We're going to use our old reliable function that we've been using for like everything in terms of like our transformations and all that. Let's think about what is happening with our function f of x equals x squared. Okay, so is this a function? Yes, absolutely it is a function. Is this function invertible? And the answer here is going to be no. How do I know that it's going to be no? Well, let's ask the question, what would f inverse of, let's say, 4 be equal to? Okay, what is this trying to ask? Well, if we're doing f inverse, then 4 is like an output of our original function, and we're looking for inputs of our original function. So in other words, what are the inputs that would give us an output of 4 here, Haddon? So not 4 because it's a square root function. 16 is going the opposite direction. This is going to be the inputs that would give us an output of 4 are positive 2 and negative 2. And that's an issue, right? We don't want a map that says turn right and end up at positive 2 or negative 2. It's a bad map. Okay, but it would still be nice to have an inverse for this function if it's possible. We'll talk about why inverses are useful to have here in a moment, but we'll just work with the blanket assumption of if there is a function that we can kind of force an inverse to work, then we would ideally like to be able to take its inverse. Okay, so right now we're running into the issue of the inputs from our original function of 2 and negative 2 give us the same y. So when we trade the inputs and the outputs, we end up with a repeated value of x for our new, right? 4 goes to 2, and 4 also goes to negative 2. If I wanted to put a nice band-aid on the solution, what's probably just the easiest way to fix this problem? Yeah, fantastic. Let's just chuck out all of the negatives. In fact, we can say, let's only consider this function when x is greater than or equal to 0. So what have we done? We have restricted the domain of our function. Is it because plugging negative values into our function is a problem? No. There's nothing mathematically wrong with plugging negative 3 into x squared. That's fine. What's wrong is when we try to take the inverse of our function, where that negative 3 now conflicts with positive 3, right? We see that same output from both. Right? And so what do? We kind of limit our view. Let's only look at the positives. Let's not even consider the fact that negative 2 is a possible input that would give us 4. Did it have to be the negatives that I threw out? Definitely not. All right. I also could have thrown away all the positives and I would have been just as happy. We also would have ended up on an interval where every single one of my outputs has exactly one input. And that is good. That's what we want. We would have no more repeating values of y if I just limit my focus to just the positives or just the negatives. Could we have constructed some weird one where, like, between 1 and 2 we look at the positives, and between 2 and 3 we look at the negatives, and then between 3 and 4 we look at the positives? Sure, but at that point, why are you introducing this headache? Let's just keep it nice and simple. Convention says, especially for this case, that, yeah, let's just throw away the negatives. Let's just not even think about the possibility of this being negative. Okay, so we restrict our domain not because there are problems with plugging in negatives, but because we want clarity when we take the inverse. Fantastic. So now we have a function that is invertible on a piece of its domain. So we would say here that x squared we can take its inverse between 0 and infinity. That's great. We can also do from negative infinity to 0. That's also fine. We're going to focus on the positives here. That does not kind of address the main question here, which is, how do we actually take the inverse? And the good news for us is that that how is baked into the definition of what an inverse is. When we were defining our inverse function, what did we actually do? What do we do to take an inverse? Well, no, just like what does it mean to take an inverse? What are we doing here? We swap the domain and codomain. What's another way to say that? We switch the x's and the y's. We switch the inputs and the outputs. That is the key to solving for an inverse function. Everywhere where we see an x, we're going to replace it with a y. Everywhere where we see a y, we're going to replace it with an x, and then we're going to solve for y. Yeah, Keenan.
So is the f like minus 4 the not minus? Does the -1 just say it's an inverse?
Yeah.
Like actually, we have to do something.
No, so this is just to say, that's a very good question.
It doesn't actually affect it.
Exactly. So this is just to denote right here. And this is actually a really good point here. This is just to denote that we are looking at the inverse of f. Okay. Now, I want to kind of make this clarification because this is a really good point that Keenan has brought up. Raising something to the power of -1 actually has a different meaning. What normally does raising something to the -1 do? Do we remember? So for instance, if I look at 2 to the power of -1, what does that do? It takes the reciprocal, okay? So I want to be very, very clear here. When we see this notation, f to the -1, we are not looking at 1 over f of x. This is not what we are looking at. We are instead taking the inverse of f. And you don't have to do anything with it. We're just saying that it's the inverse function.
I remember yesterday it was like -f, and that's how we like pushing stuff in the graph.
Yeah. And so now this -1 is basically just saying it's the inverse function. We don't actually, the -1 doesn't actually do anything to the math per se. Yeah, very good question. A very good point of clarification. This is going to be especially confusing when we do trig, go figure, a lot of setup for trig here, where taking the reciprocal of a trig function and taking the inverse of a trig function do two very different things and are denoted with very similar notation, annoyingly similar notation. Okay, really great question, fantastic. But yeah, we have kind of hammered on to the point of what do we do to actually solve this. So for f of x is equal to x squared, what are we doing? Well, this is really like y is equal to x squared. And I am swapping my x's and my y's. So instead of y equals x squared, we're really looking at x is equal to y squared. All right, my x's, my y's, my inputs, my outputs, they trade places. Now what do I have to do? Well, now I want to solve for y. For this one, it's fairly straightforward. How would I solve for y here? y squared is equal to x. How do I get y on its own? How do I undo the square? Square root, so we could take the square root of both sides. What happens to my other side of the equation when I take the square root? So I'm going to end up with like the square root of x, but do I just end up with the square root of x? Yeah, I get two possible values, right? It's either plus or minus the square root of x, which was a problem for us, but it's a problem we already fixed. What am I going to keep here? Am I keeping the positive square root of x's, or am I keeping the negative square root of x's? I'm keeping the positive. How do I know that? Well, it's just right up here. It's what we said at the start. I want to only think about what's going on when x is greater than or equal to 0. So we've restricted our look, and that avoids the confusion when it comes to this plus or minus. We've already resolved that. We're just looking at the pluses. If we had instead said, let's look at the negatives, then we would have just kept the negatives. We would have thrown away the positive. And that's also fine. That's completely valid as well. All right, questions here with our kind of setup to inverses. Basic core idea, we're switching the x's and y's. And oftentimes I will give you the domain on which the function is one-to-one. So like you don't really need to like find that for yourself most of the time. There might be a couple of questions on Pearson. I think I tried to avoid those though. The ones that are like, find where we can take the inverse. I'll try to give you that. Okay. We don't have questions here. Let's take a look at a couple of the examples. I want to actually together take a look at example 1b here, because that one's a little bit tricky just in terms of the algebra. All right. So f of x here equal to x over x plus 2. Okay. So we could definitely talk about like what we're supposed to do. What are we going to do to find the inverse of this function? All the x's are going to be replaced with y's. F of x is going to just turn into an x, and then we're going to solve for y. That's great. Before we do that, though, I want to talk about a couple of things that we can observe about this function. All right, first thing I want to notice about this function, the domain of the original function here. Are there any values that I have to throw away from my domain? Is it positive 2 or negative 2? Notice when I plug negative 2 into my function, what happens? Why do I have to throw it away? We divide by 0 when x is equal to negative 2. Okay, so negative 2 is not allowed to be a part of our domain. If we're switching our domains and ranges, what should that mean when we take the inverse function? So if negative 2 isn't part of our original domain, then when I take the inverse, it shouldn't be a part of the codomain of my inverse function. All right. So let's maybe keep an eye out. Is negative 2 going to be missing from my range? Spoiler alert, the answer will be yes. Okay. Other thing that I want to note here, x over x plus 2. This fraction, this is an interesting fraction. We'll look more at fractions like this. These are called rational functions. And there's a lot of really quick analysis that we can do on these fractions. But just at a very surface level, I would like to make the observation that this is never going to be equal to 1. It doesn't matter what x is. We're taking a number, dividing it by something that is 2 more than itself, That's never going to equal 1. It'll get really close when x gets really, really big. It's going to kind of hone in on 1. For instance, 1 divided by 102 is pretty close to 1. A billion divided by 1,000,000,002 is really close to 1. But it never actually hits 1. And so that value of 1 is missing from our range. If the value of 1 is missing from our original function's range, what kind of prediction could we maybe make about our inverse function? It's going to be missing from the domain. So we should end up with a function that doesn't allow us to include 1, and maybe in some way is never going to hit -2 as an output. We actually could use all of that information to construct what that function would look like, but let's actually go ahead. Let's see what this is going to be when I solve here. Okay, so like we said, we're thinking about y is equal to x over x plus 2. And what am I doing? They're all trading places. So all of my y's, all of my x's trading places here. So what do we end up with? Well, this is going to be that x is equal to y over y plus 2. And our goal is to get y on its own. We're going to get y equals a thing, and then we replace y with that notation that f inverse is. All right. This is not the easiest to solve. I think this is a slightly tricky equation to solve here. The first thing I would like to observe, though, is that I want to solve for y, but I've got y's in my denominator. I don't really enjoy that. I don't like the fact that I have y's in my denominator here. So I'm going to try and get rid of the y's in my denominator. What could I do to make it so that there are no longer y's in my denominator here? Multiply both sides of my equation by y plus 2. So let's start off by doing that. So this is going to be, we'll say y plus 2 times x is equal to y over y plus 2 times y plus 2. And why are we doing this? Well, that is so that this and this cancel, and we end up with just y on my right-hand side of the equation here. Fantastic. Okay, it's a little bit easier to look at now. Not quite as gross. Awesome. The other thing that I now immediately notice is that I have a right-hand side of my equation and a left-hand side of my equation that both have y. I'm trying to get y on its own. I would like to at some point be able to combine those y's. In order for that to happen, where are they both going to need to be? They're both going to need to be on the same side of the equation here. All right. Now, the other thing that I'd like to observe is that this y right here is kind of like locked inside of the parentheses. And it's hard to get at as long as those parentheses are here. So let's get rid of those parentheses. The easiest way to do that is to actually do out this distribution, which is taking this x and distributing it in to these parentheses here. So y times x, I'm going to write that as xy. 2 times x, that's going to be plus 2x, and this is still just all equal to y. All right, questions with how we got to this line here? I don't want it to just be that, oh yeah, I can look at the algebra and the algebra checks out, the math works. Questions include like, do we understand why I have done every step that I have done so far? Like the logic behind my motivations here. Or is there a line where we are getting lost? Okay, I would like to then move forward with what Haddon proposed, which is we need to get all of our y's on one side of our equation And in doing that, we want all of our not y's to be on the other side of the equation here. Okay. Some people have at this point proposed dividing through by y. I don't think that that's a bad idea. The thing that I don't like about dividing through by y is that that's going to leave a y in the denominator of this little 2x piece. And we just worked so hard to get y's out of the denominator, I don't really want to bring them back in. So there's a way without division that I can group all of my y's to one side of my equation. What's the only real thing that I need to move in order to do that? The xy term. I want to take this and I want to move it to the other side of my equation. Let's subtract xy from both sides of my equation here. Okay, what do we end up with? 2x is going to stay the same. Xy minus xy is just 0. So this is 2x is equal to y minus xy. Okay, we're actually super, super close to being done with it here. One final observation that I would like to make is that now on the right-hand side of my equation, what is everything divisible by? Everything is divisible by a y, which is a perfect opportunity to do what? Divide the whole thing by y, but I don't want to move it all the way to the other side. So let's divide a y out to the front. In other words, we're going to factor. We're going to factor out a y to the front of our right-hand side here. So still 2x equal to dividing a y out to the front. And now we have to ask the question of what gets left behind. If I take y and I divide a y out to the front, what do I leave behind? A 1. Very good. That's very easy to forget. Remember that we are dividing that y out to the front. We leave behind a 1. From xy, I divide out a y. What gets left behind? An x. Very good. Right? It's like doing distribution in reverse. Right? So instead of multiplying something through, we divide something out to the front. Okay, final step. What do I do to isolate y? Divide both sides here by 1 minus x. And what do I end up with? Well, this is going to be 2x over 1 minus x. Quick question, can these x's cancel? They cannot cancel because the denominator x is being subtracted. It's not being multiplied. Very good. Okay, fantastic. And this is our inverse function. This right here, our inverse function. Let's see if it was consistent. So we said from our original function, from our domain, it needed to not be -2. And so we expected -2 to not be a part of our range. We'll get better at this when we do rational functions, but we have 2 times x divided by -x. If that was it, then it would be -2. But notice that +1 in the denominator, that ratio is never going to quite be -2. It's always going to be a little bit off. And so, yeah, in fact, -2 is not a part of the range of this function. And then what is x not allowed to be? It's not allowed to be 1 here, which is exactly what we predicted before, right? We said, I don't have 1 in my range, so it should be excluded from my domain. And yeah, that's exactly the kind of function that we end up with here. It doesn't have -2 in the range, and it doesn't have 1 as part of the domain, which is actually pretty cool and pretty significant. What we will see is that those correspond to vertical and horizontal asymptotes. And essentially what that means is that our vertical asymptotes became horizontal asymptotes, and that our horizontal asymptotes became vertical asymptotes. Not super surprising because we've switched our x's and y's. But what's kind of cool about that, it's not just affecting the graph, it's affecting everything. All of the x's and y's, everything that has to do with x everything that has to do with y's trades places. Which is kind of neat, I think. It's kind of neat. It'll make transformations really, really nice and very predictable. Okay, I want you guys to take a stab at A and C here. For C, you're not going to be able to come up with like an equation like what we've been doing. You could either write a list of ordered pairs, or you could like draw the bubbles and draw the arrows, whichever way you prefer to kind of show that inverse mapping. But we'll take 5-10 minutes or so, take a stab at A and C. So finding those inverse functions. And then note just the for x is greater than or equal to 2. I actually overshot. It should just be for x is greater than or equal to 0. That doesn't do anything. That's just telling you that our function is invertible, that we can take the inverse of our function. All right, but you don't have to do anything with it. That's just me telling you that it is one-to-one.
Oh, yeah, this one's the exact same.
Yeah. Where did the 1 come from? Yeah, so when we look at rational functions later on, what we are going to see, and we can kind of do this algebraically, think about what happens to our function. So this is x over x minus 2. What happens to this function as x gets really, really big? As we get close to infinity, what's going to happen to this function? Well, our numerator is going to get really, really, really big. And our denominator is going to also be really, 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 really big. This plus 2 is going to matter less and less and less and less. But it's always going to matter a little bit. It's always going to be a little bit off, such that we get big divided by big plus 2. This is going to start to approach 1. It's going to get closer and closer and closer to 1, but is it ever going to actually touch 1? No, that creates a horizontal asymptote. So what we would see there is that our function is, it's going to be shooting from below, that our function is approaching 1, but flattening out. It's not ever quite able to hit 1. It pretends, it tries really hard, never quite hits. That's actually what a horizontal asymptote is it's like the function that our function wants to be at large values. It tries really hard to be 1. It's always a little bit short. On the other side, it would also be a little bit short, but it'd be a little bit short from the opposite direction. Yeah. And we'll look at that more with rational functions. The way that you can basically tell that horizontal asymptote is that way is because x divided by x is 1. Whereas 2x divided by negative x is negative 2, which is why negative 2 is not a part of our. Yeah. So this is, so think of f of x here is just y. So this is like y equals x squared minus 4 as our original function. And what we're doing with that is instead of y equals x squared minus 4, we want x equals y squared minus 4. And then we try to get y. So like here, we started with y equals x over x plus 2, and then we switched it to x equals y over y. Yeah, it is. That was just because I don't like having y's in my denominator. That's just like if I'm solving for a variable, I don't really want it in my denominator. So I got it out of the denominator by multiplying both sides by this y plus 2. And that since I did it over here to cancel, I have to do it over here to keep everything. Yeah, so then from here, notice that both of these are divisible by y. We don't want to move it over to the other side. We're happy with it being on this side, but we do want to pull it out to the front. So we divided it out to the front here. So I guess y divided by y is 1. xy divided by y is x. And then I just kind of comes out here. So we could divide it to the other side, but we like it in the numerator, so we just kind of memorize that.
How do the y get here? We're finding the y.
So it's factoring is what we're doing. So distribution would tell us that y times 1 minus x, that we could take this y and distribute it through. Right? And you would get y minus xy. What we did is that, but in the other direction. So we started with this and we moved it back to this. This is multiplying each of these by y. And so the way to undo that, the way to go backwards, is to divide each of these by y. So we're undoing distribution, basically. Get here. Yeah, you can draw like that. You could also do it as like the ordered pairs, but it's also fine. Either way, I understand what you're saying there, so that's totally fine. And yes, this is correct, but is it going to be plus or minus? No, because I said we were going to restrict ourselves and only look at positive values. So normally it would be plus or minus, but because I'm restricting our domain to make it invertible, we throw away all the negatives. Yeah. But you're right that you would want to think, is it possible? And in this case, the answer is actually no, because we just want to use it. Yes. Yep, that's perfect. You do see, so you could do a list of ordered pairs where you reverse the x and the y for each of the ordered pairs. Or you could just like draw the bubbles, and the output bubble should now be the input bubble, and the input bubble should now be the output bubble. And then you just draw the lines in the other direction. That's right. What do you mean? What is going on here? What kind of transformation do we have? With the -4 here, what's it doing? Is it being done to the inside of our function or the outside? So think of like the squares being like the function. So it's happening to the outside, so we're being dragged like down 4. What is that turned into? No, you're correct. That's correct. But what direction is that? This isn't a correction. This is simply like an observation that we're talking. So we've gone down 4 for our original function. And what do we have over here for our new inverse function? Is that happening to the inside or the outside? The x directly? Yeah, that's fair. So notice here that this f4 is being added to x rather than the square. So notice here the 4 is being subtracted from x squared rather than being subtracted from x. Here the 4 is being added to the x squared. So basically if the 4 is first being added to the x, then it's that horizontal shift. And the thing to observe here is that we've gone from a vertical shift down 4. Which direction? What? Which is kind of what you'd expect if your x's and your y's are switching. That horizontal shift should correspond to a horizontal to a vertical shift, or vice versa, which is exactly what we see. This is perfect. We actually can't split like this. We have to stay like this, and that's kind of similar to the to the cancellation thing, where because it's addition, we can't break the 4 out. If it was multiplication, you'd be able to. Here and that. Yeah. Yeah, that's perfect. Yeah.
We do the greater than.
That's just to give you a domain over which the function.
So do we need to put that in?
No. That would be because when you take the square root, what do you end up with? Plus or minus. Plus or minus. And what does that tell us to do? Well, it should be greater than or equal to 0. It's telling you.
It's just, no,
Yeah, it's telling you you keep the positives instead of the negatives. They could have also said less than 0 and then you keep the minus. Not an inverse, that is going to be a reflection. What kind of reflection is it? Yes. This one here is perfect. You can't simplify that plus 4 because it is a change. If it was multiplication, you could do that because it's addition. Yes. I'm not sure where else to go. Okay, so what did you get?
I just drew
Okay.
X to the 1.
Yeah, absolutely. And then did you switch the X and the Y? Yeah, you just switch the X and the Y. Yeah.
And then these two.
We're gonna talk about this.
Okay, I just worked it.
Okay, yeah. Okay. Are we saying yes and then that?
Yes.
Perfect. Okay. Fantastic. Let us take a look at A here. Sorry for if this was confusing. The whole X is greater than or equal to 2. First of all, this should say X is greater than or equal to 0. My bad on that. Supposed to correct that. Did not. X is greater than or equal to 2. This is just our condition to say, hey, we can take the inverse. X squared is not a one-to-one function. It has multiple y's to x's. And so here I'm just saying, let's just look at the positive ones. We're only looking at positive values for our x, which means we're only going to look at positive outputs for our inverse function. What we end up getting there should have been something like f inverse of x is equal to the square root of x plus 4. And the thing that I would like to note here is what kind of transformation did we have starting out? What is that minus 4 doing to our function? Yeah, sorry. Is the minus 4 happening to the x directly, or is it happening to our function after the function stuff has been done to it? Is the minus 4, notice we're squaring x first and then subtracting 4. That minus 4 is happening to the end, it's happening to the output, so what kind of, it's shifting down by 4. What has that turned into? Left 4. This has gone from a negative vertical shift to a negative horizontal shift of the same magnitude. We have gone left 4, where before we were going down 4. Our x's and our y's have traded places. That will work for vertical reflections and horizontal reflections. That would work probably for vertical compressions and horizontal compressions as well. We're not really going to look at those, but noting here that we have everything that has to do with x being replaced with something to do with y and vice versa. Okay, and then what do we notice about C? It ends up being the same function. So if we wanted to list out the ordered pairs, the ordered pair 1, 4 is going to turn into what? 4, 1. the ordered pair 2, 2 is going to turn into 2, 2. It's not really going to change. 3, 3, same deal here. And lastly, 4, 1 is going to become 1, 4. And if we look at those ordered pairs, we say, oh, actually, they're the same on both sides of our kind of inversion here. Right? And so it so happens in this particular case that our original function, our original map, and our inverse map are the same. This actually shows up a couple. There are a few situations in which we're going to look at one here in a second, although maybe not in that kind of explicit. Okay, questions here with example 1. Questions here about finding inverse functions. Okay. Let us then, one more thing, and then we're done. And the one thing is kind of nice. It's why are we talking about inverse functions at all? Why do we care about inverse functions? What's the big deal with inverse functions? We have looked at inverse operations, which I use a little bit loosely, but we're not going to get into that. We have used inverse operations a lot in the past. If I've wanted to undo addition, what do I have to do? Subtract. If I want to undo division, what do I have to do? I have to multiply. So we've looked at this idea of inverse operations. And now we are looking at functions that we are describing as inverses of one another. Ideally, an inverse function should in some way undo whatever is being done. Right? Specifically, we're trying to undo whatever is being done to x. Now, the way that we break x out is going to be using our new operator, composition. This is not a coincidence by any means. This is purely kind of a definition, which is to say that if I have an inverse function, or f of x and its inverse, when I compose them, all that's left is x. That is to say that f of f inverse of x is equal to x, and that f inverse of f of x is equal to x. The linguistics behind like what this is trying to say end up being kind of funny, but if you're able to track them, it ends up being just very obvious statements. So like, what is this trying to say? If I look at my first line here, this is saying like, what is the output of the input whose output is x? Well, obviously the answer to that would be x. Or below, what is the input whose output corresponds to the input of x? Also, you know, if you're able to kind of track the language there, the answer is pretty redundantly going to be x. But we can kind of think of this just in math terms as when we compose inverse functions, they undo each other. This is a definition. This is also a fantastic way to check to see if functions are inverses. We actually now are going to have two tools to check to see if functions are inverses. First tool is just going to be switching the x's and y's of one of our functions and seeing if it matches up. And now we have a second tool, which is if you compose the functions, you should just be left behind with x. Okay, so let's take a stab at, that's from yesterday. Let's take a stab at example 2 here. Looking at A, we are trying to figure out if x and 1 over x are inverses. Let's try to confirm this with composition. So what are we doing here? Well, we are taking f of g of x, and if they're inverses, what should this be equal to? It should just be equal to x. Okay, so what is this asking us to do? Well, we are taking our function f, and everywhere we see an x, we are replacing it with g of x. Well, that's fairly easy. This is going to be just g of x. And g of x, we already know what this is. This is just 1 over x. So are these functions inverses of one another? Did I end up with just x? No. I ended up with 1 over x, and so these functions are not inverses. At the very least, they're not inverse functions. They are multiplicative inverses. If I multiply them together, I'd get 1, which is a multiplicative inverse, but they are not inverse functions. Okay. What about for B here? What happens when we compose them? Well, let's maybe try g of f of x. In this case, the order shouldn't matter. You should always end up with x if they are inverses. So in this case, taking g, this is negative, and instead of x, we are going to have f of x. Minus 5 over 3. Well, f of x is just negative 3x plus 5, so this is equal to negative 3x plus 5 minus 5 divided by 3. My 5's in my numerator cancel. My 3 and my 3 are going to cancel, and my negative and my negative are going to cancel. And what am I going to end up with? Just x. And so what can I say about my functions f and g? That these are inverses. But you could have also replaced the x's and the y's for one of the functions, solved it, and you would see the exact same function as the one that we are asking. So 2 different ways to kind of confirm that with composition and also with actually just solving. Okay. This is true like 99.99999% of the time. There is one final kind of exception that we have to talk about, and that is that this is only true if f inverse of x, if the x that we are plugging in exists within the domain of the function that we are plugging it into. So for instance, let's consider an example. Let's let f of x equal 1 over x. And we'll say that it's inverse. I'll go ahead and give it to you. You can find it on your own if you'd like. It's very, very quick. It's very, very straightforward. F inverse of x is actually the same function. It's 1 over x. And let's say I want to know what f inverse of 0 is for these particular functions. The temptation is to say, well, f of f inverse of a number is just that number. This is just 0. The problem, though, if we go with our function notation, what that asks us to do, this is saying that we are taking f inverse of 0, plugging it in to f of x. This is 1 over 0. What has gone wrong? I have what am I doing that breaks math? Dividing by 0. I have a point in my equation where I am dividing by 0. This cannot happen. And so I hit this issue where I'd like my functions to cancel, but because 0 is not even able to be plugged into x, this just does not exist. There is no solution here. It just doesn't break through. This is another one of those situations where if you take the composed function 1 over x and simplify it, it looks like 0 is perfectly fine to be able to be plugged in here. But you have to plug it in before you simplify. And when you plug it in before you simplify, you see, oh, wait a minute, I am in fact dividing by 0 here. So just a couple of things to be careful of. We want to be very, very careful about when we are doing these kind of inverse functions, not jumping the gun here, making sure that these values of x exist within the domain. It doesn't show up too often, but it is just something to be cautious of. Otherwise, it should work 100% of the time. We'll see this idea again being very relevant when we look at trig functions, which is a sentence that I will continue to say over and over and over again. All right, questions here with our inverse functions. All right, so 1.6 due today for that extra point. You do not have to submit supporting work until Sunday. So I can see if you have finished the 1.6 up by today. So I will check that. But you don't need supporting work until Sunday, and then you will submit the supporting work to that box. Like I said, I will have a study guide that I will post, if not tonight, then tomorrow. Generally as well, what I do with my study guides is on like Sunday night, I will post an answer key to the study guide where I work through every problem type once so that you can kind of check your process, check your answers. If there's a problem that you've really been struggling with, see that kind of explanation one more time before the test. The way I like to do my tests and my study guides is that every single question on the study guide should in some way be on the test, and every single question on the test should in some way be represented on the study guide. I try to be very, very transparent about what I could reasonably ask you on these larger assessments. I try to be very, very clear about what you would expect to see. All right. And then survey tomorrow, you guys will tell me what is the stuff that you'd like to go over during the review day. And then the review day will be a mix of working on various study guides / other stuff, as well as the classwork. One final thing about the study guide, I mentioned this to my fourth period because I had a former student who asked about the study guides. So the study guides are homework grades, so they go into that 5% category. They make up the bulk of that 5% category. More importantly, though, or I think more importantly, I will take 5% of how you do on the study guide and add it to your test. Which is to say, if you take the study guide and you get a 100 on it, that is an extra 5 points on your test. So 3 points, also just good practice, also just tells you what's going to be on the test. So I would make that a priority over the weekend. All right, we've got about 10 minutes left. You guys are more than welcome to use the rest of this time for classwork, questions if you have them, all that fun stuff.